Every time you pull a shot of espresso, you're running a tiny industrial process. 9 bar of pressure, 93 degrees Celsius, 30 milliliters in about 25 seconds. These numbers look arbitrary, but they're not. Every one of them is there to solve a very specific problem. Let's start with the pressure. A home espresso machine pushes water at 9 bar. That's 9 times atmospheric pressure, roughly what you'd feel under 90 meters of water. Why so much? Because you're forcing hot water through a tightly packed bed of coffee grounds in about 25 seconds, and it has to contact every single particle. Drop the pressure to 5 bar and the water takes the path of least resistance. It channels, extraction goes uneven, the shot comes out thin and sour. Push it up to 15 bar, and you strip out bitter compounds faster than the good flavors can come along for the ride. 9 bar is the empirical sweet spot the industry converged on over decades. So, what is the water actually pushing against? A small, dense disc of ground coffee called the puck. And this puck is the whole reason the pressure does anything useful. It's a resistor. Grind too coarse and water blasts through in a few seconds without really extracting anything. Grind too fine, and the puck chokes. Water can't flow at all. Dial in the grind size just right and tamp it flat so the density is uniform. And now the water has to work its way through hundreds of tiny channels, dissolving oils and soluble solids on the way. This is why baristas obsess over grind size. It's the single biggest lever you have on how a shot tastes. Now, temperature, 93 degrees Celsius, just below boiling. Go cooler, say 85, and the water can't dissolve the oils and sugars properly. The shot tastes sour and thin. Go hotter, 96 or 7, and you start pulling out the bitter, over-roasted notes faster than the sweet ones. But here's the beautiful part. At 9 bar and 93 degrees, hot water can dissolve the carbon dioxide trapped in the beans during roasting. When the shot hits the cup and pressure drops back to 1 atmosphere, that dissolved gas comes out of solution as millions of tiny bubbles, held in place by the coffee oils. That golden foam on top of a good espresso, that's crema. A physical fingerprint of freshness and pressure. A quick tour of milk steaming, because the physics is genuinely clever. The steam wand works by the Venturi effect. Steam shoots through a narrow nozzle at very high speed, and fast-moving gas has low pressure, so air gets sucked in through the holes on the side of the tip. That's the stretching phase. You hear that hissing sound, and the milk volume grows as air is folded in. Once you've stretched enough, you push the wand deeper into the milk to cut off the air intake. Now the steam just heats and swirls, and the rolling motion shears all those big bubbles into tiny ones. That's texturing. The result is microfoam, milk that pours like glossy paint, not dry foam. Quick quiz. What is the ideal pressure for pulling a shot of espresso? It's C, 9 bar, high enough to push water uniformly through the puck in the right amount of time, low enough that you don't over-extract the bitter compound. So next time you pull a shot, remember, 9 bar, 93 degrees, 30 milliliters, 3 very specific numbers, 1 tiny industrial process, and a whole lot of flavor chemistry packed into 25 seconds.